right? We were doing factoring polynomials, and I believe we discussed that these multiples would be factors, and the result of the multiplication is the product. And we gave an example with a monomial times a binomial here. And if we distribute it in, right, that gives us our product. And inversely, if we were to divide this out, right, and work that backwards, that's factoring out the GCF. We get a brief discussion of that. So right now, we discussed also, I think last time we met, what the GCF was. We said it was the greatest common factor, the largest multiple that they all have in common, or all terms have in common. So I prepared some examples that we could look at. So in these examples, I want you to find the GCF. I want you to find the greatest common factor, a value that goes into all the terms. So in this first example, we have 8, 16, and 20. So I'm looking for a value that goes into 8, 16, and 20. And we all agree, I could make a mistake on this, so if I do, stop me. It looks like it's going to be 4.
Yeah, 4.
Awesome. Right, because we know 4 times 2 is 8, 4 times 4 is 16, and 4 times 5 is 20. So they all have a common factor of 4. In the next example, 55, 75, and 121.
11.
11. 14, 28, and 35.
7.
7. 8 to the third, a squared, and 8 to the fifth.
8 to the first.
8 to the first would be a common factor. 8 to the first isn't the greatest common factor.
Mm. 8 to the second.
8 to the second, right? Because if we look at this,
Oh, because it's exponents. Okay.
a to the second times a to the first will give me my a to the third.
Yeah.
A to the second times 1 is a to the second. And a to the second times a to the third gives me my a to the fifth. So they all have a common multiple of a to the second. So my GCF is a to the second. So when we have variables, it's always going to be the smallest exponent. It'll always work out that way. The smallest exponent that they all have in common. So in this next example, we have variables again. We have x squared y, xy squared, and x squared y squared. So if we're looking for a GCF in this case, we all agree it looks like it's going to be, well,
XY.
Yeah, I think so. All right, let's do it individually, right? X squared, x to the first, and x to the second. So they all have x. Y to the first, y to the second, and y to the second. They all have at least y to the first. So they all have x, y. They all have x to the first and y to the first. Everybody agree with that?
Mm-hmm.
In this next example, it says 9a squared, 12ab, 15b squared. We're looking for a GCF. We all agree?
3.
I think it's going to be 3. Right? Because if I look at 9, 12, and 15, looks like 3 is the only thing that goes into that. And here, if I look at my variables, a squared, a to the first, and there's no a here, so they don't have a in common. And the same thing with b's. I have a b here and a b squared, but I have no b in the first. So there's nothing that they all have in common in terms of variables. So it's just going to be 3. And in this example, we have 6x squared y, 12x squared y squared, and 4xy squared. What do they all have in common?
2xy.
2xy. You're too fast. Hold on, let's see. So 6, 12, and 4 is 2. It's a little tricky there. And x squared, and x to the first. So they all have x to the first. They all don't have x squared. And y. Yep, 2xy. I agree. Any questions with that one? All right, let's turn the page. So here we're looking for a GCF also. I have 5x minus y and 4ax minus y. What do they both have in common? Attached by multiplication. My GCF is x minus y. Agree?
Yeah.
Next. 3x a plus b and 9a plus b. What do these both have in common?
3 parentheses a plus b.
I agree. 3 and 9. So 3 goes into both of those, and they both also have a plus b. So we're just identifying the GCF in these examples. We're not actually doing any of the factoring. So let's see what it would be to factor these out. If I had to factor out a GCF, I'm going to leave that in case you're writing. If I have to factor out a GCF, what I want to first do is I want to identify what they all have in common, identify the GCF, and then we're going to divide it out of all the terms. Divide it out of all the terms. So in this case, I have 2x squared, 4xy, and 6y squared. So they all have 2 in common. 2 goes into 4, goes into 6, so 2. And that's it. So if I divided 2 out of each one of these terms, really I'm dividing out of 2 literally, I'd be left with x squared minus 2xy minus 3y squared. And that's how we would factor out a GCF, right? We're just taking a 2 out of each one of these terms. You want to try the next 3? I won't plow through them so quickly. I'll give you some time to work on them.
It doesn't matter the exponent of the variable.
Well, it matters in that what they all have in common, right? So my exponent here, so I have 2 a's here, I have a single a there, but I have no a's here. So in common, they don't have anything in common. But as far as the b's, I have b to the first, and b to the second. So what do they all have in common? If we just draw a little b there and a b there, and b squared would be 2 b's. What do they all have in common? They all have at least 1 b in common. So in this example, my GCF is 7b to the first. Right? They all are divisible by 7, and they all have at least b to the first. So if I were to divide that out of each term, 7b, 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 I'd be left with 2a squared plus 3a minus 4b. And these would be my factors. So I agree, let's say 9 goes into all three. So 9. And then I have x squared, x to the first, and x to the first. So they all have x to the first. Y cubed, y squared, y to the first. They all have y to the first. So if I divide that out, or I take a 9xy out of here, I'd be left with xy squared minus, divide by 9, I have 2y plus 9. And I could always check these by distributing. You could always distribute it back in, make sure it works. This next one's a little bit tricky because it looks different. But outside of that, we're still looking for what they have in common. And so it might kind of be easy because this is jumping out at you. They both have a plus b in common. If I were to take out this a plus b as a GCF, what would I be left with? Well, if those are gone, they're moved out front, I would be left with 5a minus 3b. And just on a side note, before anybody asks, right, because sometimes this is a tricky visual, but if I had, 5a, smiley face minus 3b, smiley face, right? And I said, what do they both have in common? And we all agreed they had a smiley face in common. And we took out the smiley face. We'd be left with 5a minus 3b. Right? The smiley face in our case is the a plus b. Disaster. And this next example is similar, very similar, right? Again, they have a binomial in common. So if I factor it out or divide it out, I'm going to have 2a minus 3b. And with those out front, I'd be left with 7xy plus 5. I'd be left with these two. So now that we're able to factor out the GCF, I just want to review where we're going so you could kind of compartmentalize it mentally. And it makes more sense, at least to me, if you have an idea of how this works. Right, when we're factoring polynomials, the first step is always to factor out the GCF. This will always be the first thing we do. The next thing we're going to do, once we factor out the GCF, we're going to determine the type of polynomial we have and the type of factoring we're going to have to do. So, for example, we could have a 2-term polynomial, a 3-term polynomial, or a 4-term polynomial. And with each type, there's going to be a different method to factor. So with a 2-term polynomial, we could do the difference of 2 perfect squares or the sum and difference of cubes. With a 3-term polynomial or a trinomial, there's 2 different types. There's a type that has a leading coefficient of 1 and those that do not have a leading coefficient of 1. And then with a 4-term polynomial, we'll always use what's called a grouping method. But then there's 2 different types of grouping method. There's a 2 plus 2 and a 3 plus 1. So right now we're here. And once we factor out the GCF, we're going to determine the type. And we're going to start over here. That's where we're going. We're going to start factoring 4-term polynomials by grouping. So we're factoring four-term polynomials. Since it's four-term, we're going to be using grouping. And we're going to start with using grouping 2 plus 2. So in this example, the first thing we always do is factor out the GCF if it exists. So we look to see if there's a GCF, x cubed, 3x squared, plus 4x minus 12. Doesn't look like there's a GCF in this example. So we don't have to worry about GCF. 2, even though we already stated it, I want to be consistent in our first two steps, because our first two steps are always factor out the GCF and then determine the type of factoring we're going to do, which means the number of terms and then the method of factoring. So in this case, there was no GCF. This is a four-term polynomial. We're going to factor grouping 2 by 2. So what we're going to have to do is we're going to have to rewrite this as 2 plus 2. So rewrite as the sum of two binomials. We want to break it down right here, and we want to write this as x cubed minus 3x squared plus, always plus, 4x minus 12. We always want to write it as the sum of two binomials. Once we write it as the sum of two binomials, we're going to factor out the GCF of each binomial. Factor out GCF of each binomial. So I'm looking to the left here. What do these two both have in common? They both have x squared, which will leave me with x minus 3. And what do these two both have in common? They both have 4, so I'm going to have plus 4x minus 3. Now we want to factor out the GCF from the entire polynomial. Right, you're asking yourself, what does this have in common with this? And we can see that they both have x minus 3. So I'm going to factor out the x minus 3. And if I take away or I factor out that x minus 3, or I divide out that x minus 3, I'm going to be left with x squared plus 4. And then we could always check this by multiplication if we wanted to, right? It's just a binomial times a binomial. So you would be able to check this by distributing the first term and distributing the second term and making sure it came back to the original problem, which we could see it's going to, right? X times x squared gives me my x cubed. X times 4 gives me my 4x. Negative 3 and x squared gives me a negative 3x squared. And negative 3 plus 4 gives me my negative 12. So you could distribute that back, and you could see that these will multiply to that. These are the factors, that is the product. So here's two examples of four-term polynomials. I'll give you a few minutes. You could Try factoring these by grouping 2 plus 2.
I already have a
So you can see in this one, we're going to split it down the middle. We're going to break it up into 2 binomials. We want to do the sum of 2 binomials. It always has to be the addition. Then we want to factor out the GCF from each one of these. So in this case, they both have x squared in common, which will leave me with x plus 6. And in this case, they both have a negative 2 in common, which will also leave me with x plus 6. Right? If I divide both of these by negative 2, I'll be left with a positive 6. Also, it's important to note here, at this point, the only way for this factoring method to work is if these remaining factors are the same. So as soon as we get an x plus 6 here, we know that this also has to be x plus 6 for it to work. So now they both have x plus 6 in common. I could factor that out. So I'll have x plus 6, x squared minus 2. Any questions with that one?
How did you get the x plus 6?
This one? Or this one?
Both.
I factored out the GCF here, right? They both have, in this case, they both have x squared in common. So if I divide out an x squared, right, I'm dividing both of these by x squared, it'll leave me with x plus 6. Over here, they both have negative 2 in common. If I factor out a negative 2 from both of these, right, negative 2 divided by negative 2 will give me x. Negative 12 divided by negative 2 gives me my positive 6.
Thank you.
Right, we're factoring out the GCF from each term. So in this, yeah.
Oh, you see how you did x plus 6, x squared minus 2?
Mm-hmm.
Oh wait, I put that wrong. Oh wait, never mind. I did something wrong.
Okay. All right, similarly in this next one, it's a 4-term polynomial. I look for a GCF. There is no GCF. So I'm going to factor this 2 by 2. So I want to rewrite this as x cubed minus x squared plus negative 5x plus 5. I always want to write it as the sum of 2 binomials because that doesn't change the values. Right, I could distribute this back in and come back to the original. Nothing changes. Once I write it as the sum of 2 binomials, I want to factor out the GCF from each one of the binomials. So I'm looking over here, I want to factor out the GCF, and over here, I want to factor out the GCF. So in this case, I see they both have x squared in common, which will leave me with x minus 1, right? I'm dividing both of these by x squared when you factor out a GCF. I have 2 hints here. Well, first of all, since this is x minus 1, I know that this has to be x minus 1. So I could cheat and write x minus 1 and force it to fit, which is fine. And if that's the case, that means I want to get x by itself. So I have to get rid of this negative 5. So really what I'm going to factor out as a GCF, I could see they both have 5, but I'm going to factor out the negative as well. So I'm going to factor out a -5, which just means I'm dividing both of these by -5, and I'd be left with x minus 1. And I'm lucky enough that by distributing this back in, it would bring me back to this, which brings me to the original problem. I didn't change anything. The values are all the same. And now I could see I have x minus 1 and x minus 1, which is good. I want to factor out the GCF of x minus 1. Again, factoring out means you're just dividing out x minus 1 from both of these, which would leave me with x squared minus 5. This pen is getting light. I just made one up. I'll throw it down here. Let's see. Hopefully it works. One of my spontaneous problems, sometimes they're flawed. Let's try this problem. I'll give you a little time. So in this example, my first step is to factor out a GCF. So I look to see if there's a GCF. So I have 2, 14, 10, and 70. What goes into each one of these? They all have a common factor of 2. A squared, x, and nothing. So they have no variables in common. They just have that multiple of 2. So if I factor out a 2, I'm left with a squared x minus 7a squared plus 5x minus 35. So I factored out the GCF. I identify this as a 4-term polynomial. I'm going to factor it by grouping 2 by 2. So I still have this down there. I'm going to break this up. Maybe we'll put big brackets here. So this is going to be a squared x minus 7a squared plus 5x minus 35. So I rewrote this as a sum of 2 binomials. I want to factor out the GCF from each one. So in this case, what do they both have in common? It looks like they both have a squared in common. So I'm going to take out a squared, and I'm left with x minus 7. And over here, they both have a 5 in common, which will leave me with x minus 7. I don't want to forget about this 2 out there. It's still part of the polynomial. So now they both have x minus 7 in common. I could factor out the x minus 7, and I'd be left with a squared plus 5. And I have my 2 out front. And it looks like the final answer is going to be 2x minus 7, a squared plus 5. So let's look at this example. So we're factoring trinomials, which are 3-term polynomials. The first thing we want to do is we want to look for a GCF if it exists. In this example, it doesn't look like we have a GCF. We want to identify the type of polynomial or the type of method we're going to use for factoring. This is a 3-term polynomial. And my leading coefficient is 1. The method we're going to use here, which I don't like the sound of it, but sometimes it's called trial and error, which I don't like the way that sounds because that sounds like we're guessing. But in reality, it is a reverse FOIL method. It's really a reverse FOIL method, right? We know that what makes up this trinomial is two binomials. So what we want to do is we want to create two sets of parentheses. We want to make two sets of parentheses. And then we're going to work this backwards, just like we would do if we were foiling it, right? What you put here and what goes here has to multiply to this first term. So I'm going to say we create two sets of parentheses and apply a reverse FOIL. Oh, my first term have to give me x squared. And my last term have to give me a positive 15. So let's start with that. Let's say these have to multiply to the a term, right? If we call this A, B, and C. And these have to multiply to the C term. So right away, I know x times x will give me x squared. And what times what will give me 15? Well, I have a lot to choose from. Well, not so much. 1 times 15, 15 times 1, 3 times 5, and 5 times 3. So this is where it's kind of a trial and error. Let's throw in 3 times 5, because I know 3 times 5 is 15. I'm going to rewrite what we have because it looks sloppy. So we know these two give us our first term, these two give us our last term, and it's the combination of your inners and your outers that have to give you your B term. So the multiplication of your inners, which this would be 3x, the multiplication of your outers, which would be 5x, have to combine to the B term. And we know our B term in this case is plus 8x. Does 3x and 5x combine to 8x? Sure, if this is a plus 3 and a plus 5, it'll give me plus 8x. Plus 3, plus 5. So that's my final answer. It looks like I'm going to have, am I off the screen? X plus 3, x plus 5, when multiplied together, will give me a product of x squared plus 8x plus 15. So to reiterate, when we have a trinomial in standard form, ax squared plus bx plus c, when I factor, what I put here in my first place has to multiply to my a term, and here in my last place has to multiply to my c term. And then it's the combination of your inners and your outers that have to give you your b term. So it's going to be the multiplication of these inners, the multiplication of these outers combined, which means added, but if the signs are different, it's subtraction, equal to b term. So here's two examples you could try. So in these examples, first thing I do is I look for a GCF. There's no GCF. So I see that this is a trinomial with a leading coefficient of 1. So I want to make two sets of parentheses. What I put here and what I put here has to multiply to x squared. So I'm going to put x and x. What I put over here and what I put over here has to multiply to a -5. Well, -5 or 5 in this case is a nice number because it's prime. The only thing that multiplies to 5 is 1 times 5. So I look at my inners and outers. This will give me 1x, and this will give me 5x, 1x and 5x, and I need a -4x for my b term. So therefore, this 5 has to be negative, and this 1 has to be positive. In order to get this -4, this has to be a +1 and a -5. And it works, right? X times x will give me x squared. 1 times -5 gives me my -5, and my inners and my outers will give me my -4. A +1x and a -5x give me my -4x. In this next problem, the same thing. I look for a GCF. There's no GCF. I create two sets of parentheses. What I put here and what I put here has to give me x squared. So I'm going to do x and x. What I put here and what I put here has to give me 45. So I have a lot of different combinations. I could do 1 times 45, not a whole lot, and 5 times 9. Or 9 times 5 and 45 times 1. Let's do 9 times 5. Because I see already with 9 times 5, my inners and outers will give me 15, right? 9x and 5x will give me my 14, rather. Will give me the 14 I'm looking for. So this will give me 9x, this will give me 5x. I need a -14x. So that means that these signs have to be a -9 and a -5. And if we look at it, x times x gives me x squared. -9 times a -5 gives me the +45 that I wanted. And my inners and outers give me -14. -9x and a -5x combined together to a -14x. Let's look at this one. Let's make a more challenging one here. 5x squared. I just made it up, so hopefully it works. 25xy plus 30y squared. We're going to take a second and look at that one. Right, it looks like we have a GCF of 5. We're running out of paper space here. So I'm going to have a 5 on the outside. And I'm going to be left with x squared plus 5xy plus 6y squared. When I factor out my GCF of 5. And now I see I have a trinomial with a leading coefficient of 1. So I'm going to bring down my GCF of 5. I'm going to create two sets of parentheses. What I put here and here has to give me x squared. So I'm going to use x and x. And what I put on this side, over here and over here, has to give me 6y squared. So I could use 1 times 6 or 2 times 3. And here's where you have to kind of do a little bit of trial and error. I'm going to use 2 and 3. Well, 2 times 3 will give me 6, but I need 6y squared. So I'm going to do 2y and 3y. 2y times 3y will give me my 6y squared. I look at the inners and outers, which I have limited space here. It looks like I'm going to have 2xy and 3xy, my inners and my outers, which will give me the 5xy that I was looking for. And since it's a positive 5xy, this has to be a positive 2 and a positive 3. So my final answer is 5 x plus 2y, x plus 3y. Another thing I want to note with these 3 examples that we could pull away from is that anytime the C term is positive, anytime the C term is positive, the signs will always be the same because they have to multiply to a positive value, right? Here they're both negatives, here they're both positives. If your C term is negative, the signs will be different. So anytime the C term is positive, the signs will be the same. And if you look, they'll always be the sign of the B term, right? Here my B term is negative, so they were both negative. Here my B term is positive, so they will both be positive. Always sign of B term. That's sloppy looking. Anytime the C term is positive, the signs will be the same, and it'll always be the sign of the B term. So let's look at this one. It's very similar to the one we just did. When you look at this, a lot of times it could be overwhelming to look at all these letters and numbers together. So you want to do what you know, right? You should be pretty confident with factoring out a GCF, which in this case is 2. So that would leave me with a squared minus 4ab minus 21b squared. So you should be confident getting that far. Then since this is a trinomial with the leading coefficient of 1, we're going to create 2 sets of parentheses. What I put here and what I put here has to give me a squared. So there's not a whole lot of math there. And in this case, I know my signs are going to be different. One's going to be positive and one's going to be negative. Sometimes you could put it in now. I don't like to, but so without doing very much math, you should be able to get this far. So now we're just looking for 2 values that'll multiply to 21b squared. 21's pretty nice because not a whole lot of things multiply to 21. You know, you have 1 times 21 and 3 times 7. This is why I don't like putting my signs in first. Yeah, I wish I didn't. It doesn't make a difference. I just want to show you, normally when I do it, I don't put my signs in first. So I would put my 3b and 7b, right? Because I need my 21b squared. And then I look at my inners and outers, and this gives me 3ab And this gives me 7AB. I always write it alphabetically. That's why A comes first. And I know what these have to combine to a negative 4AB. So now I could determine what my signs are going to be. Well, if this has to be a negative 4AB, then this has to be a negative 7 and a plus 3. So I like to put my signs in after. It doesn't make a difference, but it makes more sense to me when I put it in like that. Then I could see that these two give me my first term. These two multiply to my last term. My inners and outers combine to my B term. My final answer that I would put on an exam would look like that.
It doesn't matter which way you have it, right? I automatically put the 7 on the left side of the parentheses and then 3 on the other one. Like my
Right.
signs are still right.
As long as the sign comes along with it. So if I add a minus 7B and a plus 3B, it would still work. And you could always check it by multiplying it. Now it starts getting a little trickier. Now we're going to factor trinomials whose leading coefficient is not 1. Where the leader is not equal to 1. And these are much more challenging. The good news about these is that the procedure that I taught prior is the same procedure. I like to be consistent so we're not learning new things for every different scenario. So the procedure is exactly the same. So the first thing we're going to do is we're going to look for a GCF. There is no GCF. We're going to create two sets of parentheses just like before. What I put here and what I put here has to multiply to my A term, just like before. So in this case, it's not just A squared, but it's rather X squared. It's 2X squared. So I'm going to do 2X and 1X, or 2X and X. Not so bad. And similar to the problems prior, what I put here and what I put here has to multiply to the C term. So here my choices are 1 times 3 and 3 times 1. But now this is going to make a difference, which one I choose. This is where it gets kind of trial and error. So if I put a 1 times 3, I'm just guessing, 1 times 3, and I look at my inners, it gives me 1x, and I look at my outers, and that gives me 6x. This looks like it's going to be pretty good. I need a positive 5x. So if I make this a plus, which would be over here, right, because that's where that value came from, and I make this a minus, it looks like it's going to work out. So it looks like my final answer here is 2x minus 1, x plus 3. But note, I wouldn't have been able to use 3 and 1, right? It wouldn't have worked if I did 2x minus 3 and x plus 1. This wouldn't have given me my B term. So we were lucky that our first shot, we got it. But again, the procedures are going to be the same. So let's put some examples up and we'll see if we could do these. So I've written down, it looks like 7 examples here. I'll give you some time to start working on them, and then I'll work on them in front of you, and then we'll call it a day. It's hard for me to resist. Let me start some. I look for a GCF. There's no GCF. I create two sets of parentheses. What I put here and what I put here has to give me 6x squared. This is a tough problem because there's a lot of things that multiply to 6. Right? There's 1 times 6 and 2 times 3 and 3 times 2 and 6 times 1. This is an especially difficult problem because there's a lot of things that multiply to 12. These are composite numbers opposed to prime numbers. 1 times 12, 2 times 6, 3 times 4, 4 times 3, 6 times 2, and 12 times 1. So there's a lot of things to consider. So if we're just going with trial and error, I like to shoot for something well balanced, not extreme like 1 in 12 or 1 in 6. It's my own personal strategy. I would pick something like 3x and 2x. Now, once I put a 3x in here, I cannot have another multiple of 3. I can't have 3, 6, 9, 12. I can't have, and same thing here. Since I put a 2 in here, I can't have another multiple of 2 because that would create a GCF that doesn't really exist in the original problem. So now I want to choose values here that multiply to 12. Well, listing this is very helpful because I can't do 1 in 12 because I can't have a 12 over here. And I can't have a 12 here because it has a multiple of 2. 2 and 6 I can't do because I can't have 6 over here. I can't have 4 over here. I can have 4 and 3. 4 and 3 might work. I definitely can't have 6 and 2 because I can't have 6 over here, and I can't have 2 over here, and I can't have 12 and 1. The only one that works in this case is 4 and 3. I also know my signs are going to be the same, and they're both going to be negative. I want to check it. 3x times 2x gives me my 6x squared. Negative 4 times negative 3 gives me my positive 12. And my inners and outers, this is a negative 8x and a negative 9x. Negative 8x, negative 9x combined to a negative 17x. So this worked out nice. This next one's tricky. It goes against some of my techniques or procedures. There's no GCF, so I could create two sets of parentheses. What I put here and what I put here has to give me 8x squared. So I have 8 times 1, and 4 times 2, and 2 times 4, and 1 times 8. And over here for my 4s, I just have 1 times 4, 2 times 2, and 4 times 1. Now in this case, my outers and my inners have to give me 33. So this is kind of a large value that regular multiples like 2 and 4, it's going to be tough to get this with my inners and my outers. And since I have a little insight into this problem, I know it's not going to work if I use 4 and 2. I'll put it down here as 4 and 2, but I know this isn't going to work. 4x and 2x. And there's another bad thing about 4x and 2x, is that they're both even. So that means I could have no even values here, no multiples of 2 here, and no multiples of 2 here. So right away, I know I can't use 1 and 4, 2 and 2, or 4 and 1. Right? 1 and 4 will give me a 4 over here, which creates a GCF, 2 and 4. I can't use 2 and 2, because again, the multiples of 2 and 4 and 1. I'm over-explaining this. So This can't be done using 4 and 2 or 2 and 4. The only thing that'll work is 8x and 1x. And now I'm using 8x and 1x. I also know my signs are going to be the same. They're both going to be plus. I know I can't use 4 and 1 because of this 4. I can't put a 4 there. I can't use 2 and 2 because I can't have a 2 over here. My only viable choice is 1 and 4. I could check it. 8 times 1 gives me 8x squared. 1 times 4 gives me 4. And my inners and outers, 8 times 4 is 32, plus 1x is 33. These are hard problems. This next problem doesn't look as challenging, but maybe it is. Am I going to use 3 and 3 or 9 and 1? Well, let's try 3 and 3. If I choose 3 and 3 to multiply to 9, now I need multiples of 4. I could use 1 times 4, 2 times 2, or 4 times 1. One times 4, that's going to give me 12, and 3, that's not going to give me a 5. And 4 and 1 is going to give me the same thing, 12 and 3, which is not going to give me 5. And 2 and 2 isn't going to work. That's going to give me 6 and 6, which is not going to give me 5. So my problem lies with this. I don't want to use 3x and 3x. I'm going to use 9x and 1x. 9x times 1x gives me 9x squared. Should I use 1 and 4? No, that's too big because 4 times 9 is too big. 2 and 2? Nope. 4 and 1. Right, because that gives me 4x and 9x, and 4x and 9x will give me that 5x I'm looking for, right? 4x and 9x could give me a positive 5x if this is a positive 9 and a negative 4, plus 9. Plus 9, the plus goes over here because that's what's giving me the 9x, negative 4. So this would be the answer. $15x squared. For some reason, my 1 is too far away here. That's 15x squared. I'm going to try 5x and 3x. I know my signs are going to be the same. They're both going to be negative. And what I put here and here has to multiply to this 6. So it could be 1 times 6, 2 times 3, 3 times 2, or 6 times 1. Well, it can't be 1 and 6, because I can't have a 6 over here, because it'll give me multiples of 3. Can't have 2 and 3, because I can't have a 3 over here. It looks like I could have 3 and 2, that could work, and 6 and 1. These are my only viable options. I'm going to try 3 and 2. And that would give me a negative 9 and a negative 10, which will give me the negative 19 that I'm looking for. So this one is correct. In this case, it looks like we have a GCF of 5. So I'd be left with 3x squared plus 4xy plus y squared if I factor out the 5. This is actually a very easy problem. This is the best problem here. It looks hard. I love problems that look hard and are very easy. Because once I factor out the 5, I have 3x squared here. Well, 3 is a prime number. So the only thing that multiplies to 3 is 3x and x. Right? 3 times 1 or 1 times 3. And the only thing that will multiply to my y squared is y times y. Right? I could look at my inners and outers. This gives me 1xy and 3xy, which will give me 4xy. As long as this is a positive and this is a positive. Positive 1xy, positive 3xy gives me positive 4xy. But I also know that because my C term is positive, anytime my C term is positive, the signs are the same, and they're the sign of the B term. That was a great problem because it was easy. In this case, it looks like there's a GCF again. Looks like there's an X. So I'm going to have 6x squared minus 7xy minus 5y. I wrote this problem down wrong. Oh, no, y squared. I wrote it there. Y squared. So it's a trinomial. I create 2 sets of parentheses. I'm going to use 3x and 2x to give me my 6x. And now here, this is prime. It's 5, so that's a nice easy one. I could use 1 and 5 or 5 and 1. If I use 1 and 5, that's going to give me 15 for those outers. So I'm not going to use that. I'm going to do 5 and 1, 5y, and 1y will give me my 5y squared. This gives me 10xy, and this gives me 3xy. So a negative 10 and a positive 3 will give me the 7 I'm looking for. My inners and outers have to give me that B term. So my final answer is x, 3x minus 5y, 2x plus y. Not so bad, that one. So let's work through this last one. I didn't leave myself a whole lot of room. It has a GCF of x, 4x, 4x, which will leave me with 2x squared plus 3xy plus y squared. I will leave it on a high note because once again, we have a prime value here. The only thing that multiplies to 2 is 2 and 1. And the only thing that's going to give us y squared is y times y. So this is an awesome problem. For x, I create 2 sets of parentheses. 2x times x will give me my 2x squared. Y times y will give me my y squared. It's a plus. So my answer is 4x, 2x plus y, and x plus y. That's it.